Hello guys, I hope you all are doing good. I am Vaishali Kikan and we are discussing the VLSI technology. In that we are discussing the process integration, and now today we are moving towards the next process, that is the gate formation. We have already seen the transistor making in the previous video. I hope you all have seen that video. There we had discussed how we can make the transistors and how we can overcome all of the limitations which were arising while making the transistor. If you have still not watched that video, it is highly recommended that you go back, watch it first, then come to this video. So first of all, we are moving towards the requirement of the high dielectric constant material for the formation of gate dielectric, right? I was using the SiO2 for the formation of the gate dielectric. So I was using a very thin layer of SiO2. It can be used as a gate dielectric, but there is a problem with the SiO2. If I am reducing the feature size, if the device size is shrinking, then the thickness of the oxide layer would be too thin, right? So it cannot make the MOSFET work really fine, or it cannot give the MOSFET a high operational reliability at a very low voltage, even at 1 voltage. So now we have to reduce the device size, we have to reduce the thickness of the dielectric as well, and I want to operate it at high voltage as well. So for that I can use the high dielectric constant material for the formation of the gate dielectric. So we need a high dielectric constant dielectric to replace the SiO2 as the gate dielectric material when I am reducing the feature size lesser than 0.1 micrometer. So if I am having high dielectric, thicker gate dielectric, it is going to give me better prevention of tunneling and the breakdown effect, and both of them are the limitations, right? We have to avoid tunneling and the breakdown effect. For that I require high dielectric constant gate dielectric. Now we will be having larger enough gate capacitance to hold enough charge to turn on the MOSFET if I am using the high dielectric constant dielectric. So capacitance is directly proportional to the value of the dielectric constant. If I am having high dielectric constant, the capacitance is going to increase, which is going to increase the charge holding capacity, right? So the MOSFET will be having the higher charge holding capacity. Now coming to the metal gate, how we are forming the gate actually with the help of the metals. So I can use the polysilicon, I can use the metal. So now coming to the advantages of metal, if I am using the metal, it will be giving me low resistivity. I know the metals are having lower resistivity than the polysilicon also. It is having the lower resistivity, right? So whenever the gate is having the lower resistivity, it is going to improve the device speed. So my device would be working at a very fast rate if I am using the metal gate. So there is a possibility that in the future transistor making process, we can use the metal as well as high dielectric constant dielectric material for the gate formation. So this is the possible combination of metal and high dielectric constant dielectric for the formation of gate. So you can see, first of all, we are going to strip off the photoresist, right? So you can see here we have the shallow trench isolation layer, right? Here we have the polysilicon layer, right? After that we have the extension ion implantation. You can see we are forming the source and drain over here, and after that we are having the oxide or the nitride etchback, right? We are removing the oxide or the nitride that we had used here, and after that we will be having the RPCVD, right, of the nitride. So for the deposition of the nitride layer, after that we will be having the chemical vapor deposition of the phosphosilicate glass over here, right? You can see over here. After that we are going to strip off the nitride layer. You can see here we have stripped off the nitride layer, and after that we can strip off the polysilicon layer here as well. So this is how we are going to form the self-aligned gate. So there would be less problem of alignment. You can see here we have used a lightly doped drain as well. So after that we are going to strip off the oxide layer, right? Here we have stripped off the oxide layer as well, and then we can deposit the tantalum oxide. So Ta2O5 is going to deposit over here, and then we are going to do the rapid thermal annealing. After the deposition of the tantalum oxide, we are going to deposit the tungsten as the metal for the formation of metallization of the gate. So you can see after that we can do the chemical metallical polishing of the tantalum pentaoxide, and after that we have made a very smooth layer over here. The chemical metallical polishing is going to give me a very smooth layer over here, and here you can see we have the tungsten gate, and here we will be having the tantalum pentoxide over here. So now coming to the dummy gate process, which is using the metal and high dielectric gate MOSFET. So it is used for the feature size which is lesser than 0.1 micrometer IC device, and here I am using the phosphosilicate glass CMP polysilicon and oxide stripping and high dielectric constant material deposition. So why we are using the tantalum pentoxide? The tantalum pentoxide has a dielectric constant nearly equal to 25, and the titanium dioxide is having the dielectric constant up to 80. And we can use HFO2 as well. We can use the CVD plus RTA process for the deposition, and it may never be used due to the complexity of these process. But what is the advantage? Advantage is that we can use the tantalum pentoxide, which is hard to etch, and if it is once deposited, it is very difficult to etch out the tantalum pentoxide. So now coming to the traditional process, that was just the dummy process that I showed you. Now coming to the traditional process for the metal and high dielectric gate MOSFET deposition. So now the traditional MOSFET making process is in the R&D now. We are searching about the various things related to this process and how we can improve this process. First of all, we are going to do the dielectric deposition and the annealing, then we are going to do the metal deposition, then photolithography, then the metal etching, then the ion implantation, and then the rapid thermal annealing at last. But it is too early to predict which method will be winning at the end. So these are the references. These are really amazing books which you can refer for your further studies, and I hope you like this session. If you like it, please push the like button, subscribe to the channel, and also do share it with your friends. Thank you so much.